Hello and welcome to our webinar on qualifying thermoplastic composite pipes, brought to you by our experts at Element Materials Technology. My name is Laura Llewellyn and I will be facilitating today's webinar. It is my pleasure to introduce you to our presenters today, Dr. Amir Hajday and Dr. Thomas Walsh. Amir is a senior engineer at our Element Hitchin facility with over 10 years of experience in composite materials testing and qualification in the aerospace and oil and gas sectors. He specialises in life cycle analysis and time-dependent mechanical properties of composite materials, specifically in HDHP pipes. As well as running single client test programs, Amir has collaborated in several JIPs and presented his findings at international composite events and peer-reviewed journals. Amir is also a member of the committee writing the ISO 23936-4 standard on composite materials in contact with media related to the oil and gas industry. Dr. Thomas Walsh is a general manager at the Element's Houston facility with over 25 years of experience in the energy sector. Tom has been leading technology development through advanced materials, working in a broad spectrum of industries, including defence, automotive and energy. He has technical expertise in polymeric material behaviour and failure prediction, specifically in composite and elastomer materials, with broad plasticity and hyperelasticity applications. Tom is currently responsible for establishing the technical vision to complement the business vision, setting the tone and alignment with clients and their product strategies, and driving innovation in the development of services portfolio while identifying business growth opportunities. He has authored multiple papers, presented at various international conferences, holds 8 patents, and is a registered professional engineer. Thank you, everyone, and with that, I'll now hand you over to Tom.
Thank you, Laura, and welcome to everyone on the line for joining this morning or afternoon or evening, depending where you're coming in from. During today's webinar, we'll be spending about 40 minutes with you, starting with the end use of thermoplastic composite pipe products and some history of their evolution. Then we'll touch on the design cycle, including material selection and qualification, followed by testing. Finally, we'll walk through some case studies and open the channels for a few question and answer sessions. If we look at the history of pipe, let's begin with what it's really used for, which is to convey gases or liquids between 2 points. On the left-hand side, you see something like a water conveyance system. In the middle of your slide here, you'll see an offshore riser, production riser, and on the right-hand side, some fiberglass pipes. All of these are unique materials. On the left-hand side, carbon fiber. In the center, some titanium. Excuse me. On the left-hand side, some carbon steel. In the middle, some titanium with carbon fiber, and on the right-hand side, fiberglass. Most unique or most common amongst all these, they begin their lives as joints. So in between these joints, we must connect these together with flanges or any type of welding procedure. Here in the States, we have a federal organization known as PHMSA. Among their other duties, PHMSA monitors pipeline failures and the cost of those throughout the United States. Now, these won't be all the pipelines, but they'll represent some of the pipelines that carry liquefied natural gas, gas gathering, or other hazardous materials. As you see on this chart, failures across the industry have increased in cost over time to the tune of just over $2 billion a few years ago due to a pipeline failure. And these costs are remedies, including remediation, restoring, and things of that nature. So as these failures continue to mount, typically and more common, these failures occur at the joints. So when we look at the potential pipelines within the PHMSA collection, we're talking about 250 million pipe joints, which are 250 million potential failure locations. If we extrapolate that out globally around the world to these same type of pipelines, we're looking at nearly 500,000 pipe joints. Again, not including some of the more benign applications. So easily we could be discussing about 1 billion pipe joints throughout the globe. So why worry about that? Well, if we can get to a point where we reduce the joints or possibly eliminate them, we can reduce the risk of failures, the frequency of failures. So back in the early 60s to mid 60s, companies looked at how do we develop continuous pipe. And here we see an example from 1968, a trade show where a continuous pipe was being helicoptered in. This is a unique situation. It was mostly a demonstration, but this is a 2-inch diameter pipe, And you can see the spooling diameter of something like this is about the size of a helicopter, which is about 25 meters or so. Again, this is the late 60s. Obviously not a commercial application for something you have to helicopter in. Materials have evolved, technology has evolved. That same 2-inch diameter pipe today is shipped around the globe on reels that are roughly the size of a human. Here we see the reel on the left-hand side and a human stats up on a stack running the product into a downhole well. Offshore, we continue to see large projects, so larger diameter projects get spooled onto larger reels. Again, if you can see the human in this picture kind of in the center right, it gives you a scale of what we're discussing. And by continuous, these jointless pipes are now greater than 10 kilometers in length, limited mostly by the shipping constraints, whether they're on land or on water.
Okay, now we're going to talk about the advantages of the TCPs over traditional steel pipes. The main advantage of these TCPs can be listed as the reduced weight due to the high strength to weight ratio of the composites, the corrosion resistance of these composite pipes, the spoolable products, which they have a much higher capability of being spooled compared to the steel, and the higher achievable flow rates in the pipe as the inner surface is relatively smoother compared to the traditional steel pipes. And if you look at all these advantages, then it takes us to the reduced installation and operation cost, which is a major factor in the oil and gas industry today.
As we look at these thermoplastic composite pipes and we take a cross-sectional cut through them, most of these products are built from the inside out, which means we begin with a liner or a coating or a material on the inside which resists chemistry or thermal environment. So that could range anywhere from a high-density polyethylene up to a polyether ketone. Moving further outward then becomes the primary structure. Here we could have fiber reinforced thermal sets or thermoplastics, as we're discussing in this presentation. These fibers could consist of glass, carbon, Kevlar, basically any type of reinforcing material that can be used. And then finally on the outside, there's an optional polymeric jacket. And usually these are meant to aid installations or provide some level of protection to the primary structure. As we look into the design cycle of these products, we go through a material selection phase and a design phase and also a fabrication and test phase. These design variables are quite numerous, as we described in the previous page. You could have different fibers, different resins, how the fiber is laid, whether it's braided or wound, any layer thickness differences, in addition to how it's fabricated. Of course, cost comes into play, not just cost to make, but then cost to install the product, operate the product, and eventually retire it. If you think of a three-dimensional space, you can think of maybe 3 things that you think are very important to you in this product. Maybe it's tensile properties, the pressure performance, or the spooling strain that it's wrapped. That's the size of the reel. Ultimately, you go through design cycle, you create a prototype, and you test it. In this instance, you may have gone through a design cycle and found something that's not perfectly optimal. In other words, something that doesn't get you all the tension you want or all the pressure or the spooling strain. And that's only one component, that's the structural integrity of that product. You might also look at a design cycle of chemical compatibility or even thermal performance. Most critical of these is the design cycle can be a long cycle. So we look at ways to qualify this product in different performance methods and test techniques. If we look at the qualification, each of the main standards, both ASTM and ISO, have a multiple of polymers and composites testing standards, each kind of with an overarching index or a parent that they use to describe the different test methods. Here we talk about ASTM D4762 or ISO 23936. Each one of these contain literally an index of testing of composites or polymers. Below that, some API recommendations, and this one happens to be for polyamide 11, and it's used as a liner. And then NORSOC M710, which is a chemical compatibility, thermal compatibility. If we move on to the product performance, we begin to discuss standards by API, such as 15S, which is for spoolables, the 17s, which are the traditional flexible risers that are used offshore. Historically, API's 15S was not developed until the late 90s or early 2000s as these products came online. So a lot of the components to 15 SCC coming from the flexibles and the 17 standards. In addition, we have the ISO standards 13628-2 and -11 for flexible offshore risers and unbonded flexible offshore risers. We also have UCOA that plays in, Eurocord, and more recently, the certification bodies have stepped in to develop their own standards, thereby that they would qualify a product from the design stage through the testing stage and through installation to first operation. One in particular, DNV STF119, is specific to thermoplastic composite pipes for offshore applications. Now, all this would be daunting, so we typically break apart a qualification process into steps, which we call a testing pyramid. The lowest level of that pyramid, we test on a coupon scale. The second level up, we would test on small scale pipes. And then ultimately, you're testing on a full scale pipe. Now, what this looks like in a qualification program, the pyramid is a scale of testing that covers a broad range. So on a micro scale, we might be talking about how does the fiber perform relative to the matrix that surrounds it. And to give you scale, if you were to grab a human hair, that represents about the size of 20 fibers, kind of give you a scale of things. Next, we talk about taking all those fibers and putting them together in a layer with its matrix, and then orienting each one of those layers relative to each other to become a laminate. Finally, we take that laminate and we put it in a product form, and in this case, a tube or a pipe with a fixed fiber direction, which dictates performance of the product. As we look at what governs everything, on the laminate scale, we have what's traditionally called the ABD matrix. Here on the left-hand side, this can be thought of as a force that goes into the laminate. In the center, we have the stiffness matrix, the ABD, which can be thought of as a spring. And on the right-hand side, elongation or curvature that will occur in the product. On the product scale, very similar. We talk about stresses now in the product with the center matrix there consisting of C's. That's also going to be a stiffness component relative to the performance of the product. So in the product performance, we often not just look at pipe, but we also have to look at end connections and the behavior of the entire product. Here we can see product being loaded up with its end fittings to look at elongation as we pressure up, provide tension, possibly add thermal conditions to it. In addition to those, we look at the longer product as it simulating an installation, both reeling and unreeling. And here we can see the loads being applied, not just the reeling application, but also pressure and potentially an additional tensile load. All these become critically important as the composite product itself is unique. If it's not wound at what's traditionally called a neutral angle, you'll see the product either contract or expand as it pressured up, which can create interesting reactions at the end connections as we go into the field. As we look further at this pipe, coming back to the cross section, we have things that are called permeation of these polymers. Now, this is a naturally occurring phenomenon, much like helium coming from a kid's balloon at a birthday party. That balloon just won't stay inflated forever. So permeation occurs because it's a polymer. As we apply internal pressure to the inside of the pipe, we see a saturation achieved as these molecules move through the wall of the pipe to get what we call an average permeation rate through the wall of the product. This establishes not just the permeation rate, but then what occurs when we decompress the product. In other words, what happens when we remove that internal pressure. So once we achieve that steady state of permeation, we look at what happens when we rapidly decompress the product. And is there a limit to what that decompression rate can be? And that's established through a series of tests that bump right up to the onset of blistering or potentially collapse of the product. And by collapse of the product, I don't necessarily mean the entire product. When we talk about collapse, it can happen in any one of the layers of the product. As an example, again, these molecules of pressure that permeate through the wall can collect in various positions throughout the wall thickness. During normal conditions, we have a high pressure zone within the wall. We also have a high pressure zone within the ID of the pipe. If we come into a condition where we lower that pressure, we have the potential for that liner and any one of those layers to collapse due to the high pressure that's accumulated by those molecules transferring through the wall. If you run your camera or a pig or something out in the field, what this looks like is from the bore, you see what seems to be a protrusion, almost like tonsils hanging down. That's what would be called a collapse of the liner if you see that in the field.
Okay, now we're moving alongside the qualification program. It is always easier to try to break down what we're going to qualify. So as we said originally, the TCPs have two main sections. The liner, which keeps the fluid inside the pipe and away from the fiber reinforced composite body, and hence the important parameters to be tested are the permeation of the fluid through the liner and the gas escape when pressure drops, which can result in a structural damage illustrated here, ranging from blistering to cracking both composites and the liner. And then we move to the composite body, which provides the structural strength of the pipe to carry and cope with the applied loads in transport, installation, and service. And hence, the important parameters that needs to be checked are the effect of the fluid that ages the product on the mechanical integrity of the composite, which is in particular importance, and the accelerated aging has to be used for reaching these conclusion, and for that we use the Arrhenius equation by increasing the temperature relative to the Tg of the material at the time of the exposure. The effect of these transformation can be seen in the tensile specimens that are shown on the right hand side. As you can see, a perfectly ductile material on the left has been transferred into a relatively brittle failure as a result of aging. Furthermore, the effect of the test temperature on the material is of very important, because you test you have the pipeline in the field at different temperatures depending on its use, and the material behavior changes from temperature to temperature. For these applications, the strain measurement is very important. So when we test the material at different temperatures, we have to make sure that we do the strain measurement at the same time. These are normally qualified by quasi-static testing on the pipes. There are several different standards that can be used from ASTM to ISO standards to DIN standards. And then again, very important, the product is always goes through different load cycles in the field. So the effect of the cyclic load on the mechanical integrity of the part is of an importance. And then the temperature plays a role in these tests. And after that, we move to the effect of the stress rupture or creep, which means the static load that is applied on the product over the time will have some effect on the mechanical integrity of the material or the product. So some of the key players in the TCP fields are, with regards to, we can call Vitrex, Solvay, Evonik, PPG, Toray, Dow, DuPont, which are mainly supplier of the raw material and the tape. And then with regards to the product fabrications, Magma, Strom, Baker Hughes, NOV, Technip, Flex Steel, and installers can be ranging from Technip, Subsea 7, and other large construction companies which can come into the field. And then with the end users, we can call likes of BP, Saudi Aramco, Shell, Chevron, and many other companies these days are moving into TCPs because of the advantages. And all of these different segments will require qualification to some degree, because those who are manufacturing the material want to sell the material to those who produce the product, and hence have to have some basic knowledge about it. Those who are making the product would be able to qualify those for the installers, and the installer have to be able to show their end user that these are the products based on your requirements. So there is always a connection between different sections of these chart. So, examples of the compression and tension samples used in the test can be seen here. It is recommended to move from the bonded joints in tension testing and use a mechanical gripping system to ensure that the bond line is not tested. The last thing that you want is to run a lifelong test and like 10,000 hours down the line, your bonded joint fails and your test has to be suspended because you haven't tested the material itself. So on the right hand side, the picture shows a mechanical gripping alternative to the bonded joints used in the ASTM D5450. We also would like to talk about the importance of the temperature control in fatigue testing. The frequency of the loading experienced by the pipeline in service is normally much lower than what we apply in the qualification programs. And the reason being, the tests are running at higher frequency in the qualification to get a total number of cycles required for qualifying the pipe in a reasonable time. Due to internal frictions between the composite layers, the higher frequency might result in an increase in the test temperature, which can result in accelerated failure of the parts. Hence, it is vital to run an adaptive test which monitors the surface temperature of the coupon and pauses the test when the increase is beyond a set limit. This set limit is normally about 5 degrees C, and then resume the test after the temperature drops back to its original value. The stress rupture data is another time-dependent property vital for pipe qualification. The loading scenarios can be both axial, which in the picture is shown on the right, which leads to the failure of the pipe along the axis of the pipe and is normally representative of the weight of the pipe system hanging from the oil platform down to the seabed, or circumferential, which is the picture on the left and is representing the pressure inside the pipe. When the manufacturer and operator wants to certify a pipe for 25 years service, the certifying authorities will require to see the data covering the service life of the pipe over this time, especially for the time-dependent properties, one of which is the stress rupture. What is presented here is what a stress rupture graph might look like, and it is important to point out that this graph is for illustration purposes and does not represent a real life data. The pipe is tested at different stress levels, and the time to failure, which is either a mechanical failure or achieving a specific strain value, is recorded. These stress levels are defined by the experience of the test house to provide a good spread of the data over the intended period of the test. It is recommended to have a minimum of 3 data points per stress level. Then the graphs then can be extrapolated to provide an understanding of the load at the service life of the pipe. In this case, graphs were extrapolated up to 200,000 hours, which approximately is about 23 years. Then the stress levels, which below, you've got 2 levels of stress, one for the room temperature test data and one for the high temperature test data. The stress levels which below these, the required lifetime in the graph can be defined and used in the design process to ensure that the pipeline will stay in service at the time of its actual service life. If you keep the loads that are applied on a pipeline below these levels, you can kind of ensure that the stress rupture creep failure is never going to happen over the intended period of the use.
Thank you very much, Tom and Amir. We'll be moving over to our Q&A session shortly, so please feel free to submit any questions using the GoToWebinar tool to the right of your screen. But very briefly, for those of you who don't yet know Element, we are one of the largest independent providers of materials and product testing services in the world. We are also the leader in the provision of testing and certification services to manufacturers and applications of composite materials across a diverse range of industry sectors. We use both standard test methods and, increasingly, customised testing procedures and equipment to ensure your unique composite testing projects are delivered on time and to the most stringent testing standards. Our purpose is a simple one. We make certain that all of the materials, products and devices we test, inspect and certify are safe, fit for purpose and compliant. If you have any immediate questions and would like to get in touch with our experts, please use any of the above contacts and we'll get back to you as soon as possible. But we will now move over to our Q&A session to discuss some of the questions submitted by our attendees. Okay, thank you. So the first question we've had in here is, what are the limitations of testing?
Yes, I'll take that one. Obviously, there's going to be some equipment limitations, but I think more importantly, when we talk about these products and the composite materials, we often look to do accelerated aging, which means we press the materials beyond their normal use, what would be normally used in a 20-year cycle or a 50-year cycle. So our challenge in that is how much can we push the temperature or push the chemical attack to get an answer for you within a reasonable time versus having to test for 20 years. So that tends to be the limitation in testing.
Okay, thank you, Tom. Another question we've had in here: where do you do the testing?
Element is a global company. We have labs all over the world, but when it goes to composite specific to oil and gas, it is mostly concentrated around Houston in US and Hitchin lab in UK, which are the center of excellence. But we can run lots of composite testing in other labs. Depending on your location, we would be able to help you with.
Okay, thank you. Another question we've had in here: what are the different failure modes in TCPs?
So the failure modes can be numerous, especially when we're talking about composite materials. If we begin with that inner liner, you can have failure of the liner, whether that's a chemical attack or a thermal attack. Then the main primary structure can have fiber failure or resin failure. Then, of course, you have your end connections, and you can see failures in the end connections or the interface between the pipe body and the connections themselves. So, yeah, depending where you see failures or where the important part is, or maybe more importantly, which part of that product is most prone to failure, that's where you start to focus on how do I strengthen that, how do I test that.
Okay, thank you very much. That actually brings us to the end of all of our questions now. There will be a short survey that will pop up on the screen just after the webinar's ended. So please do fill that in. We'd appreciate any feedback you've got on the webinar. Thank you, everyone. Have a great afternoon and the rest of your day. Thank you. Goodbye.
Thank you. Bye.